So hi guys, welcome back to this session now. So first of all, let me welcome you again to the Unacademy JEE English. This, as you know, is a brand new channel by Unacademy, which is India's largest online learning platform for IIT JEE. And in this particular platform, every concept of physics, chemistry, and maths are being taught to you completely in English, so that no student who are feeling uncomfortable due to extensive usage of Hindi in most of the content available on YouTube are feeling left behind. All right. So this is a series that I host for class 12 students, and the topic that we are discussing right now is alternating current, and this is lecture number 4 of alternating current. And today we'll be talking about LCR circuits. So this is a very, very important topic as far as the AC is concerned. All right. So before we get started with today's lecture, let me introduce myself for those of you who don't know me yet. So my name is Rohit Dixit, and I studied mechanical engineering from IIT Delhi. And for almost past 8 years, I've been teaching physics for the JEE Mains and advanced exams now. As a student, I myself was All India rank 447 and All India rank 192 in the two stages of the IIT JEE exams that I took. So JEE also back then used to have two stages, just like you guys have two stages. So in the first stage of the IIT JEE exam, I was All India rank 192. And in the final stage, I was All India rank 447. And that's how I got admission into mechanical engineering IIT Delhi. Now, as a student, I also qualified in the NTSC stage 2, which is a very, very coveted examination. And then I was also in the top 1% of the NACP, which you guys might know as the National Standard Examination of Physics, or better known as the first stage of the Physics Olympiad. Okay. So again, now all this teaching of my 7 years has been in offline setups, and offline I've been lucky enough to have mentored and coached many students to top ranks in their JEE examinations and also in various examinations like KVPY and Olympiads. So I've helped many students reach their dream colleges and get their dream ranks. Now I hope to continue doing that here online with you guys. So how can you students make sure that you're not suffering due to this lockdown and your preparation is not only going on smoothly, in fact, it is going on better than others. So this is what you can do. You can get yourself the Unacademy subscription. This subscription will give you benefits like live classes where you get to interact with your educators on a regular basis. Then these classrooms also have live polls and leaderboards, which keep them highly interactive and very efficient. And then you have test series and analysis sessions, very, very important to keep you on your toes, to keep you aware of where you stand in the competition. And of course, you have live doubt clearing sessions. So again, a wonderful, wonderful feature. So every fourth session in all the Unacademy Plus courses is supposed to be compulsorily a live doubt clearing session. So make sure that makes sure that your doubts are never getting piled up. So hello S Pandey, hi Moti Lal, how are you? Hello ARJ, hello Forging Fire. When does modern physics start? Okay, so the modern physics I think will take a little time. Okay, so after AC we will talk about EM waves, and then we will move on to optics. Okay, so that is the plan. And after optics we will probably take up modern. So probably sometime in January. Okay, forging fire. So in January we'll be talking about modern physics. In any case, modern physics you guys study a lot in chemistry as well. So I'm sure that should not be too much of a problem. But in any case, our discussion will start in Jan. In December, we'll try to finish optics. Okay, that's the plan right now. Now, as I was saying, Unacademy subscription also gives you another very huge benefit. It gives you the chance to study from the best educators all across India from the comfort and safety of your home. Now, that is a very wonderful feature. That is an opportunity that you couldn't have gotten even in any offline setup had there been no lockdown. So this is another very great feature, a very great opportunity that you're getting with your Unacademy subscription. So what are you waiting for? Go and get this subscription. And this is how you should do it. First, you'll need to install the Unacademy app. Once you have done that, then you will go to the plus section of the app, select your goal as IIT JEE and click on that get subscription button. Now, once you do that, you will be redirected to the payment page where you will see you have two options of selecting your subscriptions. You can either go for a plus subscription or go for an iconic subscription. So your plus subscription is a regular subscription which gives you which unlocks all the lectures and study courses that are available on Unacademy. Iconic subscription takes your preparation to the next level. So when you are here at the payment page, do not forget to use this code RD Live. So this code will get you a 10% off on all your fees. And these are the prices of all the subscription fees after the discount, by the way. So the plus courses will cost you 6 months subscription will cost you 25,000. 12 month costs you 34,000, and a 2-year subscription would cost you around 50,000. The fees for the iconic for the same time periods would be 34,000, 58,500, and 90,000. When you click on proceed to pay, you will also realize that you have a lot of no cost EMI options to choose from. So even if this seems like a burden, then you can divide this payment into a lot of no cost EMI options and listen that. Yes, sir, I'll join you live from Optex, sir. Okay. Right. I asked my dad to get the subscription. He gave me a full lecture. Okay. Wow. But ARJ, you realize that the subscriptions are pretty cheap. So I don't know why should it be that much of a problem. If you're going to any offline institutes, by the way, any offline institute would charge you anywhere between 4 times to even 10 times this fees. So Unacademy is providing you this opportunity. Maybe you can even go for a 6 month trial period, right? So you can start with a 6 month subscription, ARJ, and see how it goes. That's not too much in any case, right? And then tell your dad that there are no cost EMI options available. Okay, so you don't even have to make this payment in one go. You can divide it into like 5 payments of 5,000 each for a 6 month subscription. Also, that shouldn't be more much. Okay. So as I was saying, now you also have an option of going for the iconic subscription. Okay, so what's iconic subscription? Iconic subscription will take your IIT JEE preparation to the next level. In this, with this subscription, you get assigned personal coaches and you attend a regular IIT JEE workshops. You have expert guidelines. You have a study planner, which is a great feature. I think a lot of students struggle with this, how to plan their preparation, and then you have regular text analysis sessions. So trust me, you will get personal mentoring from some of the topmost educators. So that will definitely boost your JEE preparation. Okay. Now let me also tell you that Unacademy is also now bringing for you the Unacademy Combat. So ARJ, this is another option, by the way. You can go and compete live for this quiz and win rewards. So I think first few uh, I think finishers get a complimentary Unacademy subscription also, by the way, in case you did not know about this, ARJ. Why don't you do this? You can go and compete live for the next Unacademy Combat, which is going to happen on the 20th of December. Enroll using this code RD Live in that, and do well and win yourself a subscription. So again, those of you who are really looking forward to getting a subscription, you can enroll in this. You will not only win cash prizes, you will also win the subscription. Okay, you can give this a try, RJ. All right. Those of you who are following us on the JEE English channel of YouTube can connect with us on the Telegram app using this link. So join us here and that'll make sure that you are receiving all timely notifications of all the lectures and amazing sessions that are happening on the JEE English channel, and you're not missing out on any of things. Okay, then why don't we get started with today's lecture then? So as I said, today is lecture number 4 of alternating current, and we will be talking about LCR circuits today. So yeah, I said I told him that, sir, and he told you don't know what real classes are like. When I was age, I used to wake up at 4:30 and travel 1 kilometer. Yeah, I know. Those are the kind of standard replies that you get from parents, right? So, but tell your dad, no. So if I've got a chance of studying smarter and getting better education from the comfort of my home, why not go for it? Right? I don't know. I don't know. Okay, as I said, you can even try to compete in the Unacademy Combat and win yourself a subscription, right? Go for it. Try that if you are unable to convince your dad for this. So, anyways, so the first circuit that we'll be talking about today is the series LCR circuit. So that's a circuit containing a series combination of a resistance, an inductor, and a capacitor. Okay, all connected to an alternating EMF source, which has some peak value E naught, which varies. The EMF in the source varies as E equals E naught sine omega t. So, as I said, for all these kind of circuits, we will have two methods of analyzing. We can either write the differential equations using the Kirchhoff's laws, or we can go for phasor analysis. So let's see how we would have written the differential equation using KVL KCL first. Okay. So again, at this point, you won't be able to solve these equations, but trust me, when you go into the college, okay, in your college, when you're doing a course on circuits, electrical circuits, then you will be doing those integrations, okay, and solving those differential equations, because then you would have learned how to solve these differential equations. So in this kind of a circuit, let's assume that at any instant t, the current in the circuit is I, and the charge in the capacitor is Q, and the current is changing with a rate of di by dt. So hi Raj, how are you? So assuming this is the direction of the current. Okay, so let's see what kind of KVL equation could you have formed. So assume that there was this current flowing through the circuit. Okay, this current was I. It was changing at a certain rate of di by dt as of this instant. And this capacitor had gained some plus Q charge here and some minus Q charge here. Okay. So when you're writing the equation for KVL, so first let's get started from here. So what we will do is we will start from here, cross the source first, and then move across the inductor in the direction of the current, then cross the capacitor from the positive plate to the negative plate, and then cross the resistor in the direction of the current again. So let's see how our different terms in the KVL will look like. So first I will write I have plus E naught sine omega t. Okay, and then I would have had minus L di by dt, correct? And then you would have had minus Q over C. And then you would have had minus I times R equals 0. All right. So this is the differential equation you would have gotten. So let's see what I can rewrite this as. Okay, I hope this is clear that this is L. L. So I can rewrite this as L times 2Q over dt2, okay, and then plus dq by dt times R plus Q over C equals E naught sine of omega t. Now, if you notice this differential equation, does it remind you of something? Have you seen such a differential equation before? Think about it. About it. Though you may not know how to solve this directly, but you have actually seen this kind of differential equation before. You may not remember it. This, in fact, was the differential equation for damped oscillations. Okay, this is the kind of differential equation that you get in damped oscillations. Okay, so we have a very similar differential equation for damped oscillation. So if you take up your NCRT, I don't know if you're in your NCRT, you will see the differential equation for damped oscillations. Okay, but if you do, then you will realize it is very similar to this. So very similar differential equation comes in damped oscillations also. Okay, so there is one way of solving this without actually solving this. You directly compare all the coefficients with the differential equation that you had in forced oscillations and write the result of forced oscillations, replacing all the comparable coefficients. Okay, so there is one way of solving that. That is one way of solving that. But again, you can't directly solve this differential equation because you don't know the maths for that right now. If you don't remember the result of damped oscillations, then also it will be difficult. And if you remember, damped oscillations had this huge equation as the results. Forced oscillations. Okay, sorry, not damped, but forced oscillations. Yeah, so forced oscillations had a very huge expression at the end, right? So it is very difficult to remember that also. So let's go to our easier method that we have for analyzing this. Again, the easier method would be through phasor diagrams. Okay, so the phasor diagram of the LCR circuit will be something that you can see here. Okay, so let's assume that the resistance phasor can be drawn in this direction. Okay, this is my resistance phasor. So this is the voltage across the resistance. Okay, so this will be in line with the current. Okay, so you know that the current phasor in the circuit would point in this direction. Okay, then you have voltage in the inductor, which you know will lead the current by 90 degree. So this is the phasor voltage across the inductor, right? And then you have the capacitor in which you know the voltage lags the current by 90. So then you can draw yourself the voltage phasor for capacitor. Now you know that the net applied voltage must be a sum of all these three phases, right? So I hope you realize that as L, C, and R are all joined in series, so you will know that at any instant the current flowing through all of them would be the same, right? So it would have the same magnitude, it would also have the same phase because it's the identical current. One current is flowing through all the circuit elements at one instant, right? So, however, you realize the voltages would be in different phases, which we can relate with the currents, okay, as shown. Now, you also know what is the value of this phasor. The value of this is going to be this, which represents the voltage across the capacitor. Now, the value of the voltage across the inductor would be this. This is the length of that phasor. And as far as VR is concerned, now VR would have had this value. Now you can say that the applied voltage is nothing but the final phasor sum of all these three, right? So if I add all these, then I should get the final voltage because it's the final voltage that is getting divided across all these three elements. So you realize this is the final voltage, which is actually the sum of all these phasors. So how can you relate with that now? You realize if you make the phasor diagram, you have on one side the net voltage phasor across the inductor and the capacitor, and then you have the voltage across the resistor, and the phasor sum of these would be the applied voltage. Okay, so let's try and write the expression for that. So I know that E naught, which is the length of this phasor, voltage phasor, okay, the net this should be equal to E naught square should be equal to VL minus VC whole square plus VR square. Okay, I hope you can see that from the phasor diagram, right? Now all I need to do is substitute these values. So when I substitute these values, I will realize that E naught square equals, realize this is IXL minus IXC whole square and I naught, and this would be plus I naught R whole square. So what you see is I naught. The value of the peak voltage through the current can be found out, through the circuit can be found out, which would be in fact E naught over a root of XL square minus X square. So XL minus XC whole square, sorry. So XL minus XC whole square plus R square. Okay, so this is the value of the peak voltage. Now, if you wanted to find the phase of the this voltage, you will realize that if I can find this angle phi, then my current in this case will lag the voltage by an angle phi. So I can say from that triangle that tan phi, what will tan phi be? Tan phi would be XL minus XC over R. Okay, because we can replace these values, and then I naught sin naught would have gotten cancelled, and from here I would have gotten the value of phi. Now once I know the value of I naught and once I know the value of phi, I can write the equation for the current. Now equation for the current would have become I equals I naught sine of omega t minus phi. Okay. Now you will realize all these phases would be rotating at the same omega. So that's why the I naught phasor will also have to rotate with the same omega, and it is lagging behind the voltage phasor by an angle phi, and the voltage at any instant has the phase of omega t. So the phase of the current phasor at any time would be omega t minus this phi. So this is the expression that you get for current. Now at any instant you can tell the current in the circuit. You can now at any instant tell everything about the circuit. Okay, what is the voltage difference across the inductor, what is it across the capacitor and the resistor. Okay, so this is how you would have gotten this equation using phasors. Okay, now again in this circuit the term impedance again is the term which is telling you that how the peak value of the circuit will be governed. Okay, so you will realize that I naught is nothing but E naught over root of this term, right? This is what you can call Z. The greater the Z of the circuit, the lesser is the current. So Z becomes a measure of opposition to the current that is being offered by the circuit. Okay, So this is called the impedance, and impedance of this circuit is given by root of R square plus XL minus XC whole square. Okay. Now you can also substitute the values of XL and XC in terms of omega and L. So this is the expression that you have. And of course, tan phi was this, which we have already seen. Now the impedance triangle for this circuit can also be made. So this is what the impedance triangle of the circuit will look like. So on one side you have the reactances, and on one side you have the resistor, and then the phasor sum of them will represent the impedance, okay, the net impedance. Okay, so that is how you could have gone about this also. So from here also you can see the relation that z square would be equal to xl minus xc whole square plus r square rooted. Okay. Okay, so what is ARJ saying, sir? ARJ is saying it should be xc minus xl. Okay, I mean that's what I did today in class. So you realize, ARJ, it is in square, right? It is in square. You think it makes a difference? I hope you realize. I hope you realize XL minus XC whole square is also equal to XC minus XL whole square, right? There is absolutely no difference between the two. Okay. So you can write any of them. If you're talking about the phasor though, if you're talking about the phasor, because I am talking about the phasor, in the phasor, I'm talking about the upward one. Okay, so upward, it will be XL minus XC. If you wanted to draw that phasor downward, then downward you would have drawn it as XC minus XL. So it's one and the same thing. You just change the direction of the phasor and then you can change the signs. Okay, so not a big deal. It's the same thing. Okay, it's the same thing. It depends in which direction you want to draw your phasors. Okay, if in the impedance triangle, I could have even made it like this, right? I could have made it like R here, and then I could have had a downward one, which would have been XC minus XL. It would have been the same thing. Would have been a completely same thing. Instead of making an upward thing with XL minus XL. If I change the sign, I change the direction. That's about it. Yes, yes, yes. So it's the same thing. No, it's just how you choose to draw it. Both are correct. There is nothing wrong with this. There is nothing wrong with this. They both are representing exactly the same thing. Okay, ARJ. All right. So from the impedance triangle also you could have calculated the answer. Okay, you would have known that the net voltage would have been in the direction of the net impedance in the impedance triangle, and the current phasor would have been along the resistor in a case of this impedance triangle. Okay, next let's try some questions. So questions on this are going to be very simple. The circuit looks very complex. The initial idea of analysis seems a bit complex, but once you start solving the questions, trust me, the questions are super easy. So let's try a question here. This question says you have to find out the impedance of the given circuit. So what will be the impedance of the given circuit? So try this, and this should be very easy to solve. Okay. Okay, so try this, guys. Easy one. Let's get started with some practice. So why don't you guys give it a try? Till then, I'll help myself with some water. Okay, so easy one. Very easy. You know the resistance, you know the inductive reactance, you know the capacitive reactance. All you have to do is find the impedance of the total impedance of the circuit. Okay, let's find this quickly. Okay, AP. So good to see that you're trying. Again, very simple. I hope you were paying attention. This is how you calculate the impedance, right? So all you need to do is apply that formula. Very straightforward answer. Nothing difficult about this. The topic of AC, in fact, is very simple. Okay, you will realize this. Yes, 5 would be the correct answer. You know how to calculate the Z. You know Z square equals XL minus XC whole square plus R square, correct? So XL has been given to you as a 9, XC has been given to you as 6. So you can write this as 9 minus 6 whole square plus 4 square. Okay, that is z square. So z square you will find is coming out to be 25, which will give you your z as 5. That's it. That is it. Very well done. Yes, guys. Yes. Absolutely. So this is a very, very simple kind of a problem. Okay. We start with very simple problems. Now let's try and find something else. So here you've been told you have to find out the AC emitter, find out the reading of the AC emitter, and also calculate the potential difference across the resistor and the capacitor. Okay, so let's see that. Okay, what do you think those will be? So think about this. Okay, so try this, try this. This should be easy again. This should be okay. Yes, 5 was the correct answer. Okay, okay, guys, well done. So let's move on to the next one then. So here you have to first find out the AC ammeter reading, and then you have to calculate the potential difference across the resistor and the capacitors. If voltmeters were connected across the resistor and the capacitor, what would be the resistances across capacitor and the resistor? That is what you have to find out. Okay, so let's see. 10. Okay, so let's see if that is correct. Okay, okay, 10 may be correct, absolutely. Hmm. So let's see. So let's find the impedance of the circuit first. Okay, so impedance of the circuit obviously would be Z square would be XL minus XC whole square plus R square. So that would be so 20 minus 10 and a 10. So I have 10 square plus 10 square. So I know Z will come out to be 10 root 2. Okay. Now I've got a Z, and let's figure out what naught is. E naught is your 100, right? E naught is 100. So what will be ERMS? ERMS would be 100 over root 2, right? So you know now IRMS would be ERMS over Z. Okay, I hope you guys remember this, right? So if you remember, I naught was E naught over Z. So if you just divide both the sides by root 2, then you would have gotten IRMS would have been equal to ERMS over Z. Okay, so that is what I have to find out, right? The AC ammeter will read the RMS value of the current, correct? So let's see what this is. So IRMS would have been ERMS, which is 100 over root 2 upon Z, which is 10 root 2. So that in fact comes out to be 5 amperes. Okay, so the RMS value is not 10, it is going to be 5. Okay, guys, it is 5. It is 5 again. I think Mahi ji got the first answer correct. Okay. Now, if you had to ask the potential difference across the resistor and the capacitor. So again, when nothing is specified, we always assume that we are being asked the RMS values. So again, you know the IRMS. IRMS has been known, and you will know that VR, which if you talk about the peak, then that would have been I naught times R, and IRRMS, VRRMS would have been IRMS times R. So that would have been 50 volts. If 50 volts would have been the reading across a voltmeter connected to the resistor. Similarly, what about the capacitor? So VC RMS, that would have been IRMS times XC, right? XC is 1 over omega C. Okay, so IRMS I already calculated as 5 into 1 over omega. Omega was 100 pi, and C was, okay, so XC has been given to me as 10. C has been given to me as 10, so I will find that into 10. This would be 50 volt again. Okay, so the readings across both of them, yeah, if you're talking about the reading across both, then that would be 100. But I think it is asking for individual. Okay, so I think you guys are answering. If I calculated, if I calculated across them individually, imagine, then the readings would have been 50 and 50. Okay, the readings would have been 50 and 50. All right, let's try another one then. Let's try another one. Now, the question says, calculate the impedance and the current in the given circuit. Also comment on the phase of current with respect to the source voltage. I think there should be an off here. The phase of current with respect to the source voltage. Okay. So let's see how you would do this. Okay, this should be easy. So first, let's calculate the impedance. Okay, so by now you should have gotten used to about how to calculate the impedances, right? So what will be the impedance of this? Now, please note that you have been given, this time you have not been given the reactances, you've been given the capacitance, and you've been given the inductance. So how will you do this? So should be very very simple. Okay, 100 sine t volt. It is 100 sine t volt. Pay attention to that. What is omega? What is omega? Think about this. Okay. What do you think is going to be the answer? So try and give me your answers. What do you think is the impedance and the current of the given circuit? What is the current in the given circuit? Now, again, whenever I'm asking about current, 5. Okay, so let's see. Whenever I'm talking about the current, then let's talk about the RMS value only, or we can also talk about the peak value. That doesn't really matter. Okay, so let's quickly talk about the impedance first. So you know the inductance is 1 Henry and the capacitance is 0.2 farad. Okay, so what is the omega? The voltage varies as 100 sine t. So omega is 1. Please note. In the circuit shown, in the circuit shown, omega is 1, so which makes your XL, which is omega times L, equals 1. And how about XC? XC is 1 over omega C, so that will be 1 over 0.2, so that will be 5. Now the impedance Z square would be XL minus XC whole square plus r square. So that will be 4 square plus 3 square. Yes, in fact, it is 5. 25. So z comes out to be 5. So 5 is the correct answer. Well done. Okay, so yes, now how much is the current? How much is the current? First of all, so let's talk about I naught. I naught would have been, V naught over 5. So that would have been 20 amperes. And IRMS, obviously, if you talk about IRMS, that would have been this over root 2, this over root 2, so 10 root 2 amperes. So these would have been the values of my peak current and the RMS current. So if nothing else was mentioned, I would have always gone for this. If I had to mark in my options, because it says what is the current in the circuit, so I always mark the RMS value. Please remember that. Now, what about the phase? What about the phase? So let's talk about the impedance triangle. In this case, you will have this kind of impedance, and this is 3, this is 4. So you have this as the voltage phasor. So this is the voltage phasor, E naught, or let's okay, this is what a Z, where Z points. So this angle you will realize is tan inverse of 4 by 3. Tan inverse of 4 by 3 is in fact 53 degrees. So current, it will be in this direction, and voltage, will be in this direction. So yes, in this case, current leads the voltage by an angle of 53 degree. So you are absolutely right in your answer, AP. Well done. Okay, I hope everybody followed this. If you have any doubt regarding this, then you can let me know. Okay, this is a simple enough question. So pretty straightforward, simple questions. Nothing much to worry about. Okay, just remember those phasors that we. Okay, so I can see here that the voltage lags, which, if you remember, should be easy to see. In case of inductor, you will remember the voltage leads, and in the case of a capacitor, you will know that the voltage lags. So if so, you can make a note here. You can notice one thing. Note, if XC is greater than XL, circuit behaves as capacitive. Right? It will have the voltage lagging the current, or the current leading the voltage. And if XL is greater than XC, right, circuit behaves inductive. Then you would have had the opposite thing happening. You would have seen the current lagging and the voltage leading. Okay. I hope you guys can that. Okay, so that should be very simple. Now let's move forward. Let's also talk about the resonance in LCR circuit. Now, why are we talking about resonance? You will remember that I told you initially. If you look at this equation, where was it? Yes, here. So we did talk about it. We said that if you look closely at this differential equation is exactly what you see in a case of the force oscillations. Okay, so we have a very similar differential equation for force oscillations. Now, resonance is something which was related to force oscillations, right? You would realize that in force oscillations, the amplitude of oscillation depended on the frequency of the source, right? Source causing the force oscillation. Similarly, here, what is the source of current? What is the source of power? It is the battery. So you will realize here also, of course, you will notice, because your these values depend on frequencies, right? Because these values depend on frequencies. Where were we? Yes, here you see these values depend on frequencies. So you will realize that the magnitude of current in such a circuit also depends on the frequency of the circuit. So that is why you have again something very similar phenomena as a resonance here also. So a circuit is said to be resonant when the natural frequency of the circuit is equal to the frequency of the applied voltage. So if you remember the analysis, if you compare all these circuits uh, with your oscillatory circuits, oscillatory situations. So I told you LC circuit. LC circuit was a pure oscillatory circuit, which could have been seen as an analog to a spring mass system performing SHM, right? Where the kinetic energy of the block was converted into the potential energy of the spring and vice versa. So in an LC circuit, you would see the energy stored in the magnetic field of the inductor goes into the energy stored in the electric field of the capacitor and vice versa. And there was absolutely no loss, right? So an LC circuit is your pure oscillatory circuit. You can think of it as your normal SHM kind of a situation, right? When you have damping, then that is what your resistor does. If you had only an LCR circuit without a source, then you would have seen damped oscillations. Then the current and the charge in the circuit would have gotten damped with period. Okay, so if you had this kind of a circuit, imagine your L, C, and R. That's it. No source. Initially, the capacitor was charged. In that case, the current would have shown the variation of damped oscillations. There would have been oscillations of charge in across the capacitor, oscillations of the current across the capacitor, and the magnitude would have slowly died out. So this would have been your damped oscillation circuit. Now, if you want to maintain the peak value of the current, then you can add a source which actually behaves as a forced oscillatory circuit. So what is the natural frequency of the circuit? If you remember, what would have been the natural frequency of the circuit? It would have been the frequency of the circuit without the damper, right? So this behaves as a damper. This is the normal resonating oscillating circuit. So the frequency of that oscillating circuit, that would be called the natural frequency of the circuit, and that would be 1 over root LC. Okay, so that is called the natural frequency. Natural frequency of this circuit is known as omega naught equals 1 over root LC, which we have already calculated when we were discussing LC oscillations. So this is what you call the natural frequency. Now, if the frequency of the source applied voltage becomes equal to this natural frequency, then we say that the circuit is in resonance. Why is that? So what happens in resonance in case of forced oscillations? You see that the amplitude is the highest possible, right? So similarly here, that is what will happen. You realize if you see the variation of the impedance with frequency, you realize that if frequency was zero, imagine frequency was zero, then XL would have been infinite, correct? If frequency tends to infinity, okay, so sorry, if yeah, frequency was zero, then XC tends to infinity, right? So at this point here, you will realize XC tends to infinity, right? If the frequency is zero. Similarly, if the frequency is infinite, then XL tends to zero. So at zero frequency, your circuit has infinite impedance. At infinite frequency, your circuit has infinite impedance. Somewhere in the middle, it has the lowest impedance, right? So this is the kind of variation that you would have seen here in case of your impedance. Okay, I hope you can see that. So there is a minima that is achieved. You realize that impedance. What is the impedance of the circuit? Let's think about this. Impedance is given as a root of XC minus XL whole square plus R square. Now you realize if you vary the frequency, this term is constant. Correct? This term is constant. It does not depend on frequency. The only term that can change with frequency is this. So if you want to keep the Z minimum, what you can do is you can get this minimum, and the minimum value of this term, because it's a squared term, can only be 0. So you will realize from this expression also, what is the minimum possible value of the impedance? It will be equal to Z. And when it will be equal to Z? When your frequency is at resonant frequency, which is given here at this omega. And omega is this, at this omega, XL becomes equal to XC. And that is when you would have had the minimum impedance of the circuit. Okay. So that is what we can now see here. At a resonance, you will realize XL equals XC and hence VL equals VC. These are the magnitudes that I'm talking about. The voltages are equal in magnitude. There will be on opposite phases, of course. Okay. Now phi is 0. Phi is 0 because you will realize that the net voltage now would be in the direction of the current. Okay. So if you draw the phasor diagram, you would have seen the phasor diagram for voltages. you would have seen that you would have had a VL, and then you would have had a VC. And since VL and VC are equal, so all the voltage, all the potential difference would have remained across the resistance. These two would have cancelled each other out. These two would have cancelled each other out, and this is what would have been the direction of V naught phasor also. So you would have realized in this kind of a case, in the resonant circuit, the phi is zero. That is, the phase difference would be the voltage, and the current phasor is zero. Voltage and current are in phase. The Z is minimum, which is R. Okay, and the current is of course maximum, which is V by R. Right. Now, if you notice the variation of current with different frequencies. So this again graph looks very similar to that of force oscillations, in which amplitude would vary with frequency like that. At a resonant frequency, the amplitude would be maximum. So that is what you can see in this graph. So in this graph, you will see that the value of the current changes. Okay, value of the current changes with frequency. It achieves a maxima at the resonant frequency, and then it starts to dip again. Right? This is the kind of values of currents that you would have seen here. Now we will talk about some important terms related to this. So first we'll talk about half power frequency. So what is half power frequency? So there will be two frequencies. So maximum power will be consumed at this, right? I hope you realize here is where the power consumed would be maximum, right? Because the current is maximum and all the current is going through the resistance. Again, we will discuss the entire power consumption in LCR circuits or in AC circuits in the next class. But still, you should have this idea that at this current, the power consumed would be the maximum. Now, when the current is at I max by root 2, when the current is at I max by root 2, you will realize that the power consumed would be half the maximum power. Okay. Why that? We will discuss this in detail, but you should know the only element that consumes power, that dissipates power in the circuit is the resistance. So if you reduce the value of the current by I by root 2, the power dissipated across the resistance, which goes as I square R, becomes half. Okay. Now you realize you would have had two frequencies for which the power dissipated would have been half the maximum, correct? So one you have this value, one you have this value on both sides of the resonant frequency. Now, these frequencies are called half power frequencies, okay? Because at these frequencies, the power dissipated is half of the maximum power. Now, then you also have a term which is bandwidth. So, what is bandwidth? Bandwidth is the difference of the half power frequencies, okay? Difference of the half power frequency. Then we define another term which is called the quality factor, or also known as the Q factor. Now, Q factor of an AC circuit basically gives an idea about the energy stored and the energy lost. Okay. So, what is the total energy stored, by the way? What is the total energy stored? The total energy stored maximum would be the energy stored in the inductor and the energy stored in the capacitor. Okay. And what is the maximum energy loss per cycle? So, that is the energy dissipated across the resistor, right? So, this is how you define the Q factor. Now, there is another way of defining the Q factor. And first of all, let's talk about the significance of Q factor. Now, Q factor represents the sharpness of resonance. So, why do we really want the sharpness to be high? I'll tell you why. So imagine another circuit which had the variation like this. Imagine which had the variation which was like this. Imagine this. The variation was all of a sudden higher and sharper. Okay. So for this circuit, you would have known, you would have said the Q factor. If this has a quality factor of Q1 and this has a quality factor of Q2, then for this one, I would have said Q1 is greater than Q2. Okay, Q1 would be greater than Q2. The quality factor for circuit number one would have been greater than the quality factor for circuit number two. Now, what do I mean by that? So, another way of easily defining Q factor is that you find the ratio of the resonant frequency is to bandwidth. So that is telling you that how sharply uh, the frequencies are changing. Okay, how soon does this frequency come? Okay, so the sharper the curve, the higher will be the value of this. And if you realize, if you solve this, then the value can also be written as XL over R or XC over R. Okay, because under resonance, XC and XL are equal. So this is how you can define the Q factor of an LCR circuit. Now, why does it matter? As I'm saying, why do we call this quality factor? So, what is the use of LCR circuit? If you know, a very common use of LCR circuit is in your radios. So, I hope most of you must have heard those radios, right? In which you change the channel. So, how do you think that is working? How do you think that is working? So what happens is that I'll tell you what happens. That there is an antenna which is picking up a lot of signals. So imagine there are five channels which are sending their frequencies. So let's take up 93.5, 95, and which is common one, 104, 104. So these are the FM frequencies that your antenna is receiving. Now every one of these frequencies would generate a current. Okay, so they will behave as sources of currents of these frequencies. Now all of them would have produced some currents. Okay, so when your antenna is picking up, let's say three frequencies, so these three frequencies would produce three corresponding voltages, which would create three corresponding currents. But you will realize due to this nature, if you adjust your values of C and L appropriately, then you can control the resonant frequency. Okay. So suppose my circuit is in resonance with this frequency. If I adjust my resonance frequency to this, I wanted to do. If I adjust my resonant frequency to this, to let's say 95, then what will happen is that the current generated corresponding to the frequency of 95 megahertz or hertz, whatever that is, would be the highest because it is in resonance. And you will realize the sharper this circuit, the currents due to other frequencies would be very less compared to the current due to this. So majorly, the current flowing in the circuit would be governed by the frequencies that are being received at this frequency, so which will eventually be converted into voice, which will be sent. Those current signals will be sent to your speakers, which will create a voice, and that is why your speaker would be able to pick up that frequency and make you listen to that radio station. If you change the frequency, then you can listen to another radio station. Okay, so that's how it works. And you realize the better would be the sound quality. Why? Because the better is the current corresponding to this, and the lesser is the current corresponding to these. So the signal becomes more and more pure if the Q factor of the circuit is higher. So that is why this is called the quality factor. It comes from practical purposes. Okay, if you remember those old radio sets in which you had to turn this big knob, you know what that used to do? You would be surprised. So in those old days, you had inside a capacitor, and then you had this knob. And when you turned this knob, by the way, this turning of this knob would have moved this plate of the capacitor. Okay, so in one direction, it would have made the plates go closer. In another direction, it would have made the plates go farther away. So what that does is that is changing the capacitance of the capacitor included in the LCR circuit. So if you change the capacitance, then you realize you are changing the resonant frequency of the circuit. Okay, because resonant frequency is 1 over root LC. So that is what you used to do when you used to turn the knob in those big radio sets, change the frequency, and you change the resonant frequency essentially of the circuit. So if there is any input corresponding to your resonant frequency, that would have produced a good current, which would have sent current signals to speakers, which would have produced a sound corresponding to that radio channel. So that is something very interesting that you must know. Very simple circuit, LCR circuit, such a huge advantage. Okay. So anyhow, I hope now the idea of Q factor is clear to you. So let's just go over a couple of questions for practice. This is one question that we have. So for what frequency the voltage across the resistance R will be maximum? So what should be the frequency of the source for which the voltage across the resistance will be maximum? So this is very easy to see again. Yeah, I hope you will be able to solve this. Hmm. Hmm. So let's see if you can get this right. So this is the last question that we'll be discussing today, and then we'll be wrapping up today's session. We will discuss the rest of the things about EC circuits in the next class, where we will try to wrap it up. There is two more things that I need to discuss: the power consumption in AC circuits and transformers. These are the last two things left for us to discuss. Okay, so what should be the answer of this? Hurry up, hurry up. It's super easy, okay? This is super easy. Get it done right. Can I have a quick answer? Hurry up, people. क्या कर रहे हो भाई? Let's get this done very fast. Very simple. Define the frequency for which the voltage across the resistor is maximum. Now, when will be the voltage maximum? When will be the voltage maximum across the resistor? What is the voltage across the resistor at any time? It is I times R, right? So for V to be max, I should be max. When is I max? When impedance is min. So you have to find essentially the condition for resonance only. So this is an alternate way of asking you to find the condition of resonance. Okay, that's it. They're just trying to confuse you. And I think a lot of you got confused probably because nobody seems to be giving an answer. Okay, so obviously I can say V across resistance is I times R. So since R is independent of frequency, right? R is independent of frequency. That is why for this I can say that VR would be maximum when the I is maximum, straightforward. Okay, if I also if like in case of capacitors and inductors, your XCs and XLs depend on frequencies as well, not only the current. So there you couldn't have said whenever the current is maximum, then the voltage would be maximum. No, because your XCs and XLs also depend on the frequencies. Okay, so there things would have been different. So I can say V equals IR. So for max VR, I should be max as R is constant. So I know for I to be max, I know that frequency omega should be equal to 1 over root C. Let's see how much that becomes. That becomes pi. So pi should be the omega. If you know the omega as pi, you know the frequency. Frequency is omega over 2 pi. So 0.5 hertz would have been the answer. Okay, very simple. I hope you guys followed this now. Yes, 0.5 hertz is correct. Fact. AP, well done. Okay. So this is how you would have gone about this. Okay. Now here is another practice problem. So let's so this is my favorite problem about radios. Yeah. Okay. So here is another problem which you can try as homework. Okay. So this is homework problem, and the next two problems I will discuss in the next class. So you can try this. Let's see what this question says. This says a capacitor, a resistor, and a 40 millihenry inductor are connected in series to an AC source of frequency 60 hertz. Okay, you have to calculate the capacitance of the capacitor if the current is in phase with the voltage. So, is there any news about 2021 JEE? Okay, so I told you that any news would come after 10th of December, right? So, wait for 10th of December and let's wait for the HRD ministry to announce it. As I said, HRD ministry has already announced that they'll be having an interaction with students on the 10th of December and they'll take a call on these dates after that. Okay, Ronald. So wait for 10th of December and maybe by somewhere between 10th, 11th and 15th you should have some kind of announcement about those dates. Okay. As of now, the only update that we have is one that HRD ministry is going to have an interaction with students on the 10th to discuss the dates. Second, NT has announced that tentatively, the JEE Mains would happen in February 2021 and May 2021. Okay, so these are the only two news that we have. Okay, so here you've been told if the current is in phase with the voltage. So current in phase in the voltage, when does that happen? That happens in resonance. Okay. Also calculate the value of X and I. Okay. So X, Y they haven't mentioned because it doesn't matter whether you calculate XL or XC, it would be the same. So this is what your circuit looks like. Okay. So try this. Maybe we will discuss this also in the next class. The next two I will introduce in the next class itself. And we have run over our time for today. So this is where I would like to wrap up today's session. Before I wrap it up, let me remind you that you should be getting your Unacademy subscriptions if you haven't gotten them already. And this is how you do it. Go to the plus section of the app, select your goal as IIT JEE, and click on the Get Subscription button. Now, when you're redirected to the payment page, do not forget to use this code RD Live to get your subscriptions. This code will get you a 10% off on all the subscription fees, which now you have two options. You can either go for a plus subscription or you can now even go for an iconic subscription. Okay, so the last problem was good. Yes, I know. So take it as your homework and we will discuss it in the next class, which is day after tomorrow. So, okay. Now, when you click on proceed to pay, then you will also get a lot of no cost EMI options that you can choose from. So choose a plan which suits you and get the subscription very fast. Okay. Now, as I was saying, now you also have a chance to take the iconic subscription. So what is this subscription? This subscription will take your JEE preparation to the next level. You will be assigned personal coaches and with this subscription. Then you will attend regular ITJ workshops. You will have expert guidelines. You'll have a study planner and test analysis. These are the extra features that you're getting from your normal Plus subscription. In Plus subscription, you have complete access to all the courses and all the content available on the Unacademy Plus. And in this, you are getting assigned personal coaches also, and you get these extra features. So if you want, you can definitely go for this one also. Okay. Next, let me also remind you that there is Unacademy Combat, which is going on. This is the most competitive gamified IIT JEE battle, okay, which you can compete live in. So the next Unacademy JEE Combat is going to happen on the 20th of December. You can enroll using the code RD Live and compete in this. And if you do well, you will be able to win a lot of rewards and prizes, which include cash prizes as well as a lot of subscriptions. You get a 1 year subscription, 2 year subscription, 6 month subscriptions as your prizes. So those of you who want to give these subscriptions a try can try and compete here and do well here. Okay. Next, if you like today's video, don't forget to press the like button and share it with as many people as possible. So as I said, for those who can't afford these subscriptions, Unacademy is bringing you quality education absolutely free of cost on through this JEE English channel. So make sure that you're spreading the knowledge and it is reaching all the people who need it. Okay. If you're new to the channel, don't forget to subscribe to this channel, and that is how you can keep getting and noticing studying all the amazing content available here. Don't forget to press the bell icon and to keep receiving all the notifications. And the PDF of all the slides used in today's lecture would be available for download very soon. Now, those of you following us on this channel can also connect with us on the Telegram app using this link so that you don't miss out on any of the amazing lectures and sessions that are happening on this channel. Okay, so that is it from my side, guys. Before I leave you, let me remind you one last time that if you're planning, if you like my lectures, if you like to enroll in my courses on Plus, if you'd like me to mentor you through your IIT journey, you can get your Unacademy subscriptions using this code RD Live. This will get you and 10% off, and then I can see you in all my Plus courses. Now, as I keep saying, IIT JEE is one of the most competitive exams in the world. So to crack it successfully, trust me, you will need all the help that you can get, and there is no better help available as of now other than this Unacademy subscription. So go get yourself that edge over your competition. Get the subscription now. Use the code RD Live. All right. We will take forward our discussion that we are ending today, day after tomorrow. So I'll see you then. Till then, you guys keep practicing and keep studying hard. Take care. Bye bye.